Today, I'm going to talk about a tissue that we all have, we used on the way here, but you probably never heard about before. This tissue calls the enthesis. The enthesis is the connective tissue between tendon and bones. And in this talk, I will be focused on the Achilles enthesis, which goes right here. When we think about it, this is not an easy task. We have tendons on one side, which are elastic, like rubber bands, and we have bones on the other side, which are rigid, like stones. So to put them together, you need a super glue, or a more sophisticated way, which is the enthesis, which forms a gradient of elements between them. Here, what you can see is an histology section of Achilles mouse. And on the top, you have the tendon, which is connected to the bone by a formation of fibrocartilage. It's a special kind of cartilage, which is also divided into two. We have the unmineralized fibrocartilage, UFC, and mineralized fibrocartilage, the MFC, because we need it to be both strong but also elastic. Okay, but this complex structure becomes a problem when we think about injuries. Unfortunately, entheses are also prone to injuries, mostly among professional athletes, but also among the age of 50, and can never heal. The current medical solution is suturing it back. It looks painful, huh? And it's not strong enough. It's kind of like carpentry. Sorry for any orthopedic surgeon that is in the crowd. But because we don't know much about the enthesis, it's hard to repair it because it's kind of like solving a puzzle without a picture, without a reference. So in my PhD, my aim was to gain better understanding of what is this tissue and what makes it so unique. So I began with taking enthesis from Achilles of mice. I took down this part. I dissociated into single cell and sequenced their transcriptome. It means that we are looking what kind of genes are expressed in every cell of this tissue to understand what makes it so unique, what makes it itself. Next, I used bioinformatics analysis to understand what are we looking at. And the idea is to solve the puzzle, to see what can we learn from it. So once I finished my experiment, it was 2 years ago, I ended up with tons of cells. Well, not tons, it's small tissue. But I had to wear my detective hat on and to understand where are those enthesis cells. I don't have markers for them. We began with using databases that exist from other models, and we gave the cells automated annotations. Each dot you can see here represents one cell, and cells that are located together, it means that they are similar. So most of the cells here are immune cells or blood cells, but one group really stood out as the candidate for the enthesis cells. We have chondrocytes, which are the cells of the cartilage, and fibroblasts, which are connective tissue cells. So we took those cells out, and I've generated two lists of genes. Because we know it's a tendon that connects into bone with cartilage in the center, we would expect to see tendon genes and cartilage genes. So here, each cell got a score. The dark purple, it means that it's got a high score of the tendon. And you can see the distribution of like two sides. We have one side is the tendon, like as you saw in the histology, and the other side is for the cartilage. But interestingly, we saw an overlap in the center, and I guess we would expect that because it's a transitional tissue. But this method was biased. It's genes that I choose from the information that I know. So we wanted to have it more sophisticated or professional. So we also generated a list of the most variable genes, and we used a mathematical calculation called Pearson correlation that puts genes that are usually expressed together and to give us a genetic print. So what we can see here is that we have three modules. One is for fibroblast or tendogenic, which are the tendon cells. We have in the center, you see this small rectangle of mineralization-related genes. And the other big one is the chondrogenic one. So if we go back to our, the cell U map, the map, and the histology, we have on the left side the highest score for fibroblast or tendogenic module, as we would expect in the tissue. On the other side, we have the chondrogenic module, which again follows the same logic, no surprises. But if you had to ask me, so where do you expect to see the mineralization score? I would say, yeah, sure, here, next to the bone, right? But no, it was actually in the middle. It was in the integration area where the UFC sits. So, isn't it weird that the unmineralized cells express mineralization-related genes? And if we take all of this information in a scheme, we know that we have the tendon and the bone and the fibrocartilage in the center. The fibrocartilage itself is divided into two, the unmineralized region and the mineralized region. When we looked at the tendon score, we saw that the highest level of tendon genes were located in the tendon, decreased in the UFC, and were absent in the mineralized tissues. Cartilage score, however, was peaked in the mineralized fibrocartilage, the MFC, and the mineralization was actually highest primed in the UFC, dropped in the MFC, and started to rise again in the bone area. So what we think that happened here is actually this. While the UFC cells need to undergo mineralization to transform into mineralized fibrocartilage, they need to have the ability to undergo mineralization, so they need to increase mineralization genetic program. However, once it's done, we don't want the mineralized fibrocartilage to continue to develop. We don't want it to become a bone. So immediately, this genetic program drops, and those cells increase back up the chondrogenic program because it needs also to retain cartilaginous. So, to conclude this, we understand that in order to form this unique structure of the different zones along this axis, we need to interplay between genetic programs. And here I'm showing that we are focused on the tendon, cartilage, and mineralization genetic programs. But because of lack of time, I can tell you that we found many more interesting things that I hope that you will be able to read soon. But we also found markers for those different layers. Now we have, for the first time, molecular analysis, detailed analysis for the different regions. And I really hope that all of this information could help us to solve this puzzle, to gain better healing capacity. I hope we could repair those entheses to have better lives for all of us. So I want to thank you all, most importantly to my collaborators, my lab members, of course, my collaborators, Neta and Sharon, and my super bioinformatician, Tzvi Hollander, and my advisor, Ellie. Thank you.